we're just going to set up integrals today. We're not going to finish them all the way because that's not what we want to practice. You have your Math 9s for a lot of these, or you have them, to do it without a calculator. So that's not going to be our focus. Today is just going to be our focus of setting it up. So what we're going to do today is, all week, we're going to do volume. Today, the volume will be volume of slices, which are called cross-sectional slices. So last year I brought knives to your class and I started slicing different vegetables up and like showing the different slices that you could put it back together, right? You slice a cucumber, you're going to get a bunch of circles, put all the cucumber slices back together, you have the whole thing as your volume. Think of like a block of cheese, and you can slice off different slices of the cheese, put it back together. You have a block shape or a wedge shape. That's the idea. So there are different, we do this when we slice watermelon. There's different reels I've seen pop up. They're like, this is the best way to slice watermelon. People have their own. Some people like circles, some people like rectangles, some people like triangles. You're slicing. Either way, that doesn't change the volume of your watermelon. But it's different ways to slice it, which make different shapes. Okay, if you put slices together that aren't uniform, if you put slices together that are changing in size, predictably, like following a pattern, but they change in size, then your three-dimensional object will be what's called graduated. So it starts out smaller on one end and then gets bigger, or maybe it's going to be big on both ends and then smaller in the middle, but it follows a predictable pattern. You can generate these by computer simulations as well, just to see the different slices. So the process is this. Pick one slice and describe its area. Okay, it should be a slice at random. You should be able to describe the area of that slice. If it's a triangle, you'll have to describe the base and the height of the triangle. If it's a circle, you'll need to describe the area of the circle. If it is a rectangle, you'll describe the area of the rectangle, but pick one. Once you have one, then you can integrate the group of them to turn it into volume. So that's the idea. All right, so find a volume for one slice. And then integrate that AX, which will turn into volume. It's the accumulation of all the slices put together. The slices are paper thin. They have no width. And so the slices are all put back together, infinitely many of them, to form volume. All right, so let's tackle this. So suppose you are supposed to do semicircular slices formed by sine 2x. Okay, semicircular slices formed by sine 2x. So you want to pick one. Okay, let's just focus on one of these semicircles. And we want to figure out the base of that semicircle. And so if you're looking at the picture, I picked at random the largest one right here. Actually, I should just pick a random one. Pick this one. So the corners, one corner is on the x-axis, the other corner is on the sine curve. So if I were to translate that over here, I would say that that corner is at a, 0. I don't know where position A is on the x-axis, but I know that because it's touching the x-axis, its y value is 0. So that corresponds to this one right here. I'll say that's at position A. So its coordinate is a, 0. The corner on the other side also has a value of A, but its y value is being traced by the sine curve. And so the y value of that would be 2 sine of A. So if you know where your corners are, if one corner is a, 0 and the other corner is a, 2 sine A, then the base is going to be 2 sine A. But if I want to do area, I need to convert that into radius. So the radius would be half of the value of the base. So the radius would be 1 sine A. And then the area for a full circle would be pi r squared, but for a half circle would be 1/2 pi times the radius I just found of the sine of A squared. So it's finding the area of any randomized slice along that. Now if I want to make this volume, I will set up an integral. My volume will go along the bounds from 0 to pi, and I simply take the same area slice, 1/2 pi times the sine of, and because I'm working in the variable x, I'll be the sine of x, quantity squared dx. You can pull out the 1/2 pi out to the front because they're both constants. And then you'll be left with the quantity of the sine of x squared dx. And then you'd run that through Math 9, and then you would have your overall volume. Did I go too fast through that? Anybody need to see that again? Okay, let's try another one. This is a pyramid that's been turned on its side, but its cross sections are square. We know that the largest square is 3 meters high and 3 meters wide. So squares all around. So I want to think about, as we try and figure out the one slice, like the red slice that's in the middle, I actually kind of want to think about the end here. If I make like a plus through here to figure out the height and the width, how high does that go above the x-axis? Well, let's look at the one I'm actually, yeah. That one's going to go up to 1.5, so it'll be 1.5 up. It'll also be 1.5 down. So the height, that's in the ratio. Okay, but it's coming out from, it's still 3 units away from the origin. So if I'm going all the way to here, that's still 3. And then going up is only half of that, it's 1.5, and going down is 1.5. So as you think about that, that is going to impact how you write your height and width for your randomized one. So if we come and we want to think about the height and the width that way. So if it is x position away from the origin, then my height is going to be half x, and then the bottom is going to be negative half x. So the total height is still going to be x all the way. So I'm going to have my height is half x plus half x, right? Half x up, half x down for a total of x. So my width will be the same because these are squares. So we want to just be thinking about preserved, that ratio, that proportionality is preserved because these are similar squares in proportion all the way through. So then I move on to the next slide and we find, okay, so then I just need to take that height and the width, and my area is going to be basically x times x, or x squared. My limits of integration will be 0 to 3. And so my volume I'll set up would be the integral from 0 to 3 of the expression for area dx. So it ends up to be a pretty simple Integral, this would be one you would do without your calculator. And you'd find the antiderivative and then evaluate it from 0 to 3. So we're not going to finish it, but this would be something like without your calculator. So we could do one with our calculator and one without. Any questions on that? Okay, so now there's no pictures. We're going to have to come up with our own pictures. Here we have volume formed by a base that's x equals y squared. So it's not y equals x squared. What would y equals x squared look like? Parabola. Okay, what does x equals y squared look like? It's sideways. So as you draw this, you're going to want to lay it flat, and it's going to have a parabola going that way, and then part of the parabola going that way. Okay, so it's sideways, and then we have basically a z-axis going up and underneath. Okay, we are forming square cross sections, but the squares have been turned so that they look like diamonds because the diagonal of the square is parallel to the x-axis. Parallel to the y-axis. So it's going to be like this. That's parallel to the y-axis. That's the diagonal of the square. So the square is going to come up and down and then be underneath. So that is supposed to be a square thing, but the diagonal is going across. So really we're looking at something like this. Didn't draw that so great. A little bit better. Okay. All right, so let's figure out where these corners are, the most important corners. So if we come out to position A, then we should be able to figure out the corners across the diagonal of this square. And so up here, this is going to be A, comma, and its y value. Okay, so now we got to figure out, do a little conversion here. Remember that x equals y squared is the same as y equals plus or minus rad x. Those are two equal expressions. So this top one is a rad a, and the bottom one is still a. It's a away from the x-axis, but it's negative rad a. So my corners here are a rad a on one of them, and positive a, negative rad a on the other. So that's going to help us figure out our diagonal. So my diagonal is 2 rad a. But I'm going to have to do some geometry also to figure out the hypotenuse. Like it's like all these mini right triangles in there. So I need to know how long the sides are. I really need to figure out like that for a square, so I can figure out once I know, because these are squares. Unless you happen to know the diagonal formula for the area of a square, but most people don't remember that. But we know that this is going to make a little baby right triangle. So we should be able to figure that out. We know that this is rad A. We know by symmetry that has to also be rad A. So you can use Pythagorean theorem to figure out the hypotenuse of that little baby right triangle in there. So if we do a little a squared plus b squared equals c squared, we'll have rad a squared plus rad a squared is going to equal the hypotenuse squared. So that'll be a plus a, or 2a. So c is the square root of 2a. So now we know that this is 2a, and so is this. So that gives me the length and the width of the square. So once I have that, then I can have area. So my area would be rad 2a multiplied by another rad 2a, which is just 2a. So all of that to tell me the area of one slice using this parabolic base with diagonals, squares, cross sections is 2a. So then I can finally write my volume. I was given the bounds 0 to 9. And then we'll take 2x, which is the same as 2a, and we'll integrate it. We don't have to do anything. Once we've got 2x, or 2a as our expression, we don't have to do anything to it, right? Just that's what we integrate. And you could do that one by hand as well.
Why is the area? Isn't it rad 2a times 2 rad a?
No.
Because times
The area of a square is one side times another side, not times the diagonal. Okay. All right, any questions on that? Okay, so same shape, and then we're done. Now we're gonna have, so same base. We'll try and draw our same base here. Parallel to the y-axis, best we can. And we want to draw rectangles this time. Oh, gosh, I love rectangles. They're the easiest ones. Rectangles, but they're twice as tall as the width. So we've got some pretty tall rectangles going up here. But the corners are going to be the same as what we were dealing with before. So we know that that corner is rad A, and that corner is negative rad A. So my base is 2 rad A. So my base is 2 rad A. My height is twice as tall, which means my height will be 4 rad A. And then my area will be 8A when you multiply those two together, base times height. And then setting up your integral, limits of 0 to 9, integrating 8x dx, moving along the x-axis.